So welcome, everyone, honored guests, trustees, the Carmell and Kimmeldorf family. Welcome to the inaugural Roneet Carmell Memorial Lecture. I'm your MC tonight. My name is Nancy Young. I am the Senior Director of Development for UCI Health Advancement. So I have the pleasure of working with the 50-plus doctors in the Department of Neurology at UCI School of Medicine. And my job is to find ways that the community, grateful patients, and everyone that's part of this community to support the incredible clinical research and education mission of the Department of Medicine. And it was in this capacity that I met Gary Carmell, who most of you know, or at least some of you have worked with him or are in your family and friends. It was in this capacity that I met him at a time that was both difficult and yet so inspiring. To be part of Gary's decision to create the Roneet Carmell Memorial Endowment Fund in perpetuity at UCI as part of the healing process was beyond an honor for me. And this lecture was designed to bring public awareness for the incredible research being done here at UCI by our incredible doctors in epilepsy and other neurological disorders, in cardiac arrest, coma, stroke. We do anything and everything for neurological disorders. So before I hand you over to our first speaker, I just wanted to acknowledge one of our trustees tonight, Dr. Philip Anthony with Decision Quest, who is our sponsor, our part sponsor for tonight. So I just wanted to say thank you. We also have our trustees, Madeline and James Irvine Swindon. Hello, thank you for coming. And I'll introduce Gary and the whole family in a little bit later, but I just wanted to quickly introduce our interim director of the Department of Neurology, Dr. Tassine Mozavar, who will welcome everyone on behalf of UCI.
Thank you, Nancy, and what a wonderful crowd. I think it's really heartening to see the support that the community gives to UCI and the Department of Neurology. I'm Tassine Mozaffar. I'm currently the interim chair of neurology and have been the interim chair for the last 22 months or so. But I've been on faculty since 2000. So it's been 19 plus years that I've been on faculty here. And I've really seen this program grow tremendously over the last 19 years. We have gone from a faculty of 18 people when I first started in 2000 to now 51 people. Really doing incredibly well. We're the third largest department in the school currently. And in terms of research and NIH funding, which is one of the measures of research success, we are the top department in the school right now. And a lot of it is related to people like Jacqueline and Yama, who've done incredible work, not only being excellent clinicians, but also being very good scientists and excellent scientists on that. I've known both of them for over 15 years. Jack joined the faculty in the early 2000s. He came from UCLA where he was doing his fellowship training. And prior to that, he was at San Diego for his training and Northwestern for his medical school. Yama, on the other hand, was a medical student here. He did his MD PhD here. We did his PhD work with Frank LaFerla, and then went on to UCLA, to Hopkins, and then decided to come back home to Irvine. And it's been incredible seeing him grow and grow his research and grow his clinical program as well. They're both amazing clinicians. They're both amazing scientists, and they will tell you a lot about that. But overall, if you look at the department, we've, as Nancy said, we've are doing some incredible work. We have cutting edge research, we have cutting edge clinical trials, We have specialty practices in each of the subspecialties of neurology, and provide an excellent service to the community. And we get referrals from all over the region, including Riverside as well as northern San Diego County. So I think this program will continue to grow. We have active recruitments going on right now, and the department continues to grow in terms of research. So I won't take much more of your time. I want to thank you again for your support to the program, and for coming out on a Thursday evening. Thank you.
So thank you, Dr. Mozavar. So now I'd like to show you a very meaningful video I think you'll appreciate.
I decided to start the Roneet Carmell Memorial Endowment Fund to support a particular doctor at UCI, Dr. Yama Akbari, along with Dr. Lin, who has been very instrumental in terms of taking care of our son Jacob, who has had many years of dealing with epilepsy in the aftermath of a stroke that he had at the age of 2. I have a personal belief that when I'm involved in philanthropy or even in business, I like to back really, really passionate people with great ideas who share my values. So it's really backing people, ideas, and values.
We had the pleasure and honor of meeting Dr. Akbari in the hospital, and he was kind and compassionate, and we hope that with his research that there'll be a protocol to save people in Roneet's situation so that nobody else has to suffer like we're suffering.
My mom would be overjoyed that something in her name would be helping so many people who are suffering from inexplicable tragedies. She's just the funniest, brightest, most loving person, and she had such a big heart. So to have so much good come out of her in her passing, I think would make her really happy.
To me, she was always about seeing the good and the positive, and I hope from something that was so horrible and so tragic that maybe something good and wonderful will come from the research that's being done on her behalf.
She was absolutely a life force. One of the things that I'm very hopeful about for this whole project and research and foundation is that discoveries will be made that actually will be able to bring that force of life back to other people in the same situation.
And I will honor her forever. And I am so grateful for the people and the doctors who are going to do what they're doing. And because the mind and the brain and the spirit of her is so big and so huge, and we can't ask for anything more in a human being. And she gave it.
And this is Roneet to us and to everybody else.
If she saw this endowment, she would really think this is a positive thing for the world and how people can change from it, how they can learn from it.
And I'm very proud of Gary for what he is doing in Roneet's memory, and I hope that many people will benefit from this. And it would bring joy to all of us to see that it would be helpful.
I was so fortunate to be associated with Roneet in my lifetime and how she made me better. I think Roneet would have been very proud to know that she would be associated with these two great doctors, doing such important work in such a critical area, which is the brain, could potentially change the world.
What a wonderful and lovely woman. She inspired, I think, everyone, not just her family, but her whole community and everyone around her. And what a great loss. But fortunately, tonight, our event is called Transforming Tragedy into Hope, because that is what her husband, Gary, has done. Gary, as I said before, is probably a friend or a family member to many of you tonight, but if you don't already know him, then you're about to meet a man who inspires many people through his philosophical writing and work in investing and wealth creation. He's also a man with a clear sense of meaning and the importance of having a mission. So without further ado, please welcome Mr. Gary Carmell.
Thank you, Nancy. Appreciate it. I want to thank everyone for coming out. It's such a meaningful event and very personal to me, so I really appreciate your attendance. And want to thank Nancy and Freddie and Gail at UCI, along with Mijanu Pham, who's been a terrific event coordinator, who's done so many things for us at CWS, and she and Roneet work very closely together, so I really appreciate your help on this event as well. So the two doctors speaking tonight have been instrumental in our lives, as I alluded to a little bit on the video. First one, Dr. Lin, has been very important in the care of our son Jacob. And while Dr. Akbari was very important in terms of helping us through very difficult times when Roneet had her very tragic accident. So I'm going to spend a little time talking about Jacob and Dr. Lin, and then Dr. Lin's going to do his presentation, and then I'll come back and introduce Dr. Akbari. So when Jacob was 2, he had a very rare reaction to the chicken pox that culminated in him having a stroke. And it was a very harrowing experience for us. That day is a day we'll never forget. And he was in the intensive care unit. His brain started to swell, and the ER doctor that was, leading the case said that he was really within about 30 minutes of not making it. And but due to the incredible intervention among the doctors and the care that he got, he was able to pull out of it. And he was in the hospital for 14 days. And we didn't know what was going to transpire for the rest of his life. How would he be, physically, emotionally, mentally, and but. Never underestimate the indomitable will that Jacob has. He is a remarkable person who's always very optimistic, and he's come through with flying colors. Now, the one thing that has been a residual, besides some of the physical issues he contends with, is epilepsy. So this first appeared on the scene for Jacob when he had a seizure, kind of out of the blue, when he was 8 years old. And over time, he's, of course, been on anti-seizure medication. And as he's gotten older, that medication has had some debilitating effects. He was very tired and lethargic, and he was on some very heavy doses. And we really, particularly Roneet, who would do anything for Jacob, and she was so involved in his medical care, was just committed to finding a solution. And in a very fortuitous sequence of events that I don't have time to talk about right now, we were able to come in contact with Dr. Lin. And it's embarrassing to admit, but Dr. Lin's an epileptologist. We didn't even know that field existed, and Jacob had had epilepsy for 15 years. That's how underserved it is for actually a disorder or impairment that is more widespread than most people think. So there's a huge need for more people to be entering this field. And so he has really done a tremendous job, in terms of trying to find the right mix of medicines for Jacob so that he would, regain his strength and his energy. And so this was a pretty long and arduous process. It took about 2 years for Jacob to combination of being weaned off certain medications and being put on other ones, and at the same time having seizures. He basically couldn't drive for most of those 2 years. And Roneet would essentially be there for him every day to drive him around when she was available. And it was really remarkable, her commitment to Jacob and his health and recovery, and there wasn't anything she wouldn't do for him. Her commitment to Jacob was absolutely unwavering. So when Dr. Lin and Nancy and Dr. Akbari and I came together to talk about the planning for this event, we obviously wanted to pick a day when we were all available and where we could have a great turnout if possible. And it became clear that really May was the month that was going to be the most practical month to have it. And once it was aligned on May, I was laser focused on having it on this day. I wanted it on May 23rd, 2019. So why was this so important? Well, this is the day Jacob had his stroke 24 years ago. So this is Jacob today here. And that's with Dr. Lynn. And Jacob, if you can just stand up and wave. So today, Jacob is a college grad. He has a master's in coaching and sports administration, and he's a basketball coach. So congratulations, Jacob. And so without further ado, I would like to introduce Dr. Jack Lynn. Thank you.
So thank you, Gary. That was a very kind introduction. And, I had the personal pleasure of meeting with Roneet, and her commitment to Jacob and everything that she's done has just been incredible. But also she's an incredible human being. So, and then the most recent thing I learned is that Jacob drove to Palm Springs all by himself. So I'm going to start talking about epilepsy a little bit. And epilepsy is a very common neurological disorder. And I don't know if many people know, but it's the fourth most common neurological disorder. About 150,000 new cases diagnosed every year. And 3 million people in the United States are experiencing epilepsy at this moment. But these numbers really don't speak to the individual people who are affected. It's not just a bunch of brain waves going out of whack. In fact, you can see that 1 in 26 individuals develop epilepsy at some point in their lifetime. So it is you, it is your family, it is the people that you love that also are affected with epilepsy. And that is why we need to think about epilepsy as the whole, rather than just the disease itself. So how far have we come to treat people with epilepsy? Well, the good news is that about 2/3 of the people become seizure-free on seizure medications. And that is the most common way of treating epilepsy. So if you take the first drug, about 47% of people become seizure-free. Second drug, 13%, and third drug, 4%. But interesting enough, after a person has tried 3 medications and they've not responded, the chance of the 4th, the 5th, the 20th drug just will not work. So this was a study that was done in 2000. Where are we now? Well, as you can see, let me see if I can see the pointer. This white line is where that study was done. At that time, there were not too many drugs. You have here carbamazepine, valproic acid, and lamotrigine, but those are the 3 main drugs. And now, this is a study that was just completed in 2018, where now you have lots of drugs. Shouldn't we be doing better? Should more people become seizure-free just on medication? I wish that's the case, but that's actually not the case. So this is, over here, with all of these different drugs, still about 50% of the people become seizure-free with the first drug. After you try the first drug, the second drug, about additional 13% of people become seizure-free. And then again, the third drug, another 4% or so. Almost the exact identical number 20 years from the original study. That was a groundbreaking study. So let's talk about the 2/3 of the people like Jake who's able to become seizure-free on medications. I think Gary already alluded to this, but one of the most important aspects of treating people with seizures is that what are the side effects? And how the side effects affect one's quality of life? We talked about driving, we talked about fatigue and unable to perform, in sports or just walking and so forth, concentration. Those are the things that a lot of physicians tend to overlook. And all they ask is, have you had any seizures? And you said, no? Well, thank you, goodbye, here's your refill. All right? And that's been but this study was also done around the same time as the first study. And what you can see is that more side effects you have with a medication, the lower the quality of life. And what does that translate to? Can't drive, too tired, can't work, can't have time, quality time with your family. That is what's translated. So how do we move the bar from here to here so that it can better quality of life? That's what's important for this group of people, because it's not counting the seizure. In fact, if you just count the seizures, there's no relationship with the quality of life. And people don't understand that. This study's been out for decades, but general neurologists and others don't really have a grasp on the importance of side effect of medication. So that's point number one. But for the other 1/3 of the patient I talked about over here, unfortunately, medication just won't work, and things haven't changed for the last 20 or 30 years. So what we need to do is to take a deep dive into the brain to find the source of the seizure. Because, here's the paradigm. Either you're going to continue to have seizures for the rest of your life, or somebody's going to try hard to find where that seizures come from. And the key for a physician is never to give up on your patients, no matter how many times you try. And the people, many of you over here, that are my patients, we don't stop trying, right? But it's not an easy task, right? You have 86 billion neurons in your brain, and they're firing at a millisecond interval. And that's good because you got to make fast decisions. You got to think, you got to react, and so forth. That's for survival. But that's also bad when they all fire together, culminating into a firestorm or a seizure. So what we're going to do? Well, we're going to talk about a very special person that I had the pleasure of meeting about a year ago. I'm going to call her Sleepless in Southern California. Well, why is she so sleepless, right? Well, so she's at that time I met her, she was 25, and she was having seizures since the age of 8. And what's going on with her is that her seizures only occur mostly occur during sleep. But she has this very interesting way of having seizure in which she'll raise her arm like a ballerina. And she'll have multiple of these seizures a night, almost every night. Imagine you never had a good night of sleep since the age of 8. What would that feel like, right? She was on she tried 5 other seizure medications, and that didn't work. And then when she came, she was on 3 different medications. But the problem is that her brain looked absolutely normal, and her doctors kept on telling her, there's nothing wrong with you because your brain looked normal on the MRI, and your EEG is normal. So, can we play the video? This is what our friend looked like. Can you get the video? That's it. But these will occur over and over again at night, leading to sleeplessness. So what are we going to do? Well, we did take the deep dive into the brain. So these are electrodes. They are needle electrodes that can pierce through the brain to find where the seizures come from. And what the good thing about these needle electrodes is that it allows you to take a large survey of where the seizure is coming from. We had a pretty good idea that these seizures come from the part of the brain that controls motor, because she raised her arm. But it's more of a motor planning area. So that's what we focus on. But we didn't know if it was coming from the right side or the left side, deep part of the frontal lobe, or on the side. So what we did was we put in these electrodes deep inside the brain, as you can see in the X-ray. And this is the MRI. And they created these little holes. And what we were fortunate enough to find was that we found a spot. And that's really like a needle in a haystack. Because the MRI, everything is normal. We found that spot. But we don't know exactly how big of the spot is, because this is just a survey of the brain. So what are we going to do next? Well, after that, we took out the needle electrodes, and then she went home, and then she came back for a second surgery. And what we did was we put in this grid to map out exactly where the seizure is coming from. So now we know the seizure is coming from this side of the brain, right? And then now we have to find out the exact location of where it's coming from. And this is a map of, so we found out this little area where the seizure is coming from. But also, we need to find out whether that area coincides with functional part of the brain, such as motor, which is what we're most concerned with for this patient. And when we mapped it, we sent a little electrical stimulation on these grids, and then we see if we find a twitch, a movement. And so it could be a movement of the hand, so we know that's hand motor, or a face, it could be face motor. And once we mapped out, what we found was that the greens are the clear areas, no motor activity. The yellow are complex motor planning areas, but then the oranges are actually primary motor. And you can see that there is a couple electrodes that coincide with the leg motor area. So I had a very long talk with our patient and the family, and it really took a lot of talking because the chances of making her weak is there. But what she told me was that I'd rather be weak than still having seizures. So here's the brain. So here's the electrode, and this is Dr. Frank Su, our chairman of our neurosurgery department, who did this. The electrodes were removed, and then we mapped out the motor area in the operating room again, just to confirm it. And this is the small area of the brain that was resected. It's about, this over here is about 2.5 centimeters, but the entire part is about 4 centimeters. And I'm allowed to show this because she's the only patient that I know who loves the age of Instagram, Facebook, and everything else. And she said that, I'll let you do the surgery only if you give me as many videos and as many pictures as you can. And as soon as I gave her these, it was on her Facebook. So many people have seen it. But joking aside, she did come out with a little bit of weakness, but she recovered quickly. And but we will talk more about her in a little bit because the most important thing is she's seizure-free. Okay. But while she was in the hospital, we had these electrodes inside her brain. This is the only way we can record and understand what does the brain do at the level of a single neuron, at the level of neuron population, neurons firing. When you think, what is the brain doing? That's the critical question. And there's very little research in this because all the things that we do to figure out this is done in rats, it's done in monkeys, but we're not rats, we're not monkeys, right? But therapies are derived from understanding of rats and monkeys, essentially. This is the only way we can figure out what is the brain doing. And it's unethical, obviously, to put electrodes in people who are healthy. We put these electrodes to map out the seizure area, but it also gives us a chance to figure out about how do we think, how do we talk, how do we understand. And so the typical way is that there's a laptop in front of the patient. While these electrodes are implanted inside the brain, these electrodes are connected signal through a computer, and we're recording the brain signals at precise milliseconds as a person do these tasks. And this is where the altruism comes in. She pretty much owns a record of how many experiments she did. She did 27 experiments in 7 days, and we don't compel anyone to do it. But if they feel like they want to do it. So this is essentially the people, my colleagues at Berkeley and I, we ran out of experiments for her to do. She's like, don't you have anything else you want me to do? And she did a variety of studies, and I'm very fortunate in sharing some of these studies that she may or may not be part of it, because this is an ongoing study where we recorded now about 100 patients. But these studies have provided incredible insights into a variety of things that you and I care about, hopefully, and have been published in very important high-impact journals, such as the Proceedings of the National Academy of Science, which the building over here is named after, where we understand about memory and precision of memory, and also about rewards and addiction, about emotional processing, how do we process emotion in natural communication, and more recently, about how do we understand emotional memory in neuron, and also about language. So I'm really very, very excited to share these important findings that I believe one day will have incredible implication for you, me, and everyone else. Because all of us will age, all of us will have some sort of memory decline, even if it's age-related. All of us will have sleep problems. I'm going to talk more about sleep. And someday, hopefully, through all of this, we'll be able to help other people through the altruism of patients with epilepsy. So without further ado, one of the things I've been particularly interested in is this 2 areas of brain. To me, these 2 areas are what makes us human. What makes us human is our emotion and our memory. Without those 2 ingredients, we're not very different than other animals. And so I've always been interested and fascinated in this little area called the medulla that shapes like, there you go, that shapes like an almond, and the hippocampus, which supposedly shapes like a seahorse. So how do they talk to each other? That's the fundamental question. Okay. So one of the first things, we could play the movies. So what we did, one of the very first experiments was to show our patients horror movies along with peaceful scenes. The other movie too, on the right side. Hello? Anyway, you get the idea. These are movie clips from movies such as Silence of the Lamb and so forth. So why do we do this? There you go. Well, the reason we did this was because we want to figure out how does this area of the brain communicate when we process fear. Because fear is what's quintessentially important to us because we need to survive and escape from fear. But too much fear is what makes people depressed. It's how we get PTSD and so forth, right? And so what we learn is that this signal of fear gets to the almond or the medulla area about 115 milliseconds before the hippocampus. And not only that, but when we process fear, the medulla is talking to the hippocampus only in this graph shows it in a more scientific way, but they only talk to the hippocampus in one direction, as if you're holding a megaphone and say, you're screaming at it. And this is what happens when we have overwhelming fear that debilitates us. And so if we can reverse this abnormal communication in this one direction of a megaphone speech, then hopefully one day we can help people with depression and so forth. So I'm going to run through these fairly quickly. There are a lot of details, obviously. So the other thing is about emotion and memory, and this is pertaining to PTSD and memory disorder. So if today you came over here, you drove your car, you probably park in the parking lot. But if you got mad at your significant other sitting around, you start screaming at them, and next thing you know, you got really angry and pulled into the parking lot. When you come out later on, you may forget where you parked because the emotion so overwhelmed the memory as if the amygdala is screaming at the hippocampus, as I show you. So how do we do that? And why is that important? That's important because this is exactly the mechanism happening in PTSD. If you think about a veteran coming from Afghanistan, and I'm sitting here, and if I happen to just drop something, I'm making a really loud thump, probably should make it louder, that person may relive an experience that person may have had in Afghanistan when there was a gunshot wound, and the whole thing gets relived. That's called pattern completion. We complete a pattern that is very similar, but not exactly the same, and there's a reliving of experience. So we need to understand the mechanism of that pattern completion and pattern separation mechanism, okay? So every day we walk through life, we need to separate this pattern. So if there's no emotion, these two are two different representations, even though they're two the same thing. But if there's emotion, like this burning building, they're not the same, but they sort of look the same. And you may get confused about what they're like. So this is a little video game, the game that we asked people to play. So what we did here was we show these patients pictures over here, and we asked them first to just code it as negative, neutral, or positive. So this is negative, neutral, positive, right? Then we show them a bunch of pictures, and at the end of this task, we said, surprise, there's a memory component to it. Then we show them a bunch of pictures, and we ask them, was this an old, means that you saw over here before, or a new picture? we're particularly interested in these very similar but not exact same pictures because these are called the lures. And when you can see the performance over here, when it's without emotion, these very overlapping similar pictures, they can differentiate it about 80% of the time, which is pretty good. But when you put in that emotion, boom, it's almost chance level. So emotion really, it makes you remember the whole thing, the gist of it. Like, but what it doesn't make you remember are the little details. And that's what's important. So, can you play the swing video? Hello? See, I hate it. I have no control over this. Okay. So the brainwave, that's how we talk. The brain, two different areas communicate by waves. So imagine if you go to the park, you have your kid. One kid get on the swing, start swinging. The second kid got on the swing and start swinging. And the third kid got on the swing and start swinging. In the beginning, they're completely out of sync, right? But as they start swinging, things become in sync. They start talking to each other. They're in the same rhythm. That's exactly how the brain talks to each other, are these rhythmic brain waves. And they have to be synchronized when they talk to each other. So what we realize is that when they are correct, this is the correct form, the amygdala and hippocampus are oscillating in a much slower wave, about 4 times per second. And when they're incorrect, they're oscillating in a very fast rhythm. And that's exactly, so this is the communication between the amygdala, the emotion, and the hippocampus, the memory center. They're oscillating and talking to each other in this 4 times per second rhythm. But when they're incorrect, false alarm, when they pattern completed, they are talking to each other in an 8 cycle per second. So now we can actually precisely see how 2 areas of the brain, inside the brain, talking to each other when they either correctly discriminate between very similar experiences versus not. So this is sort of a cartoon of our friend amygdala and hippocampus. So again, when they get correctly a very similar experience, they're oscillating this theta rhythm or 4 per second rhythm, and they're talking to a double communication way. But when the little amygdala gets angry, again, it's very fast and it's a one-directional shouting. So how do we correct that to get to this? One of the ways we do it is by electrical stimulation, and we have found perhaps a way of sending a wave there that corrects this rhythm so that they'll become more like this. And that's the idea of how we translate understanding of why to real technology that can help people. The other thing that we've been very interested in is speech reconstruction. And by the way, the little pictures up there are the people who did the work, not me, okay? So the first work is by my grad student, Jie Zin, who's right now a postdoc at Harvard. And this is Brian Paisley at UC Berkeley. And he's been doing a lot on speech reconstruction. Because one of the problems is that people with stroke in the speech area or people with Lou Gehrig's disease, they lose their speech. So imagine, but they don't lose the understanding of the speech or the imagination of speech. They understand, they just can't say it. The motor part of the speech is not there, right? So can we get that back? Well, one of the things, experiment we did was a fairly simple experiment where we asked people to repeat a word and then imagine it in the head. And the incredible task is, can we take that electrical activity when they're imagining that word, put it into the computer algorithm, and spit out real words? So next, so listen to this. First is spoken. This.
Structure. Doubt. Property.
Okay, so the first set is actually just speaking. The second is we ask the patient to imagine the word Waldo and take that electrical signal while they're imagining the word Waldo, put it in the computer, and spit out that word. And it's not perfect, but it's pretty close, right? So how do we make it perfect or better? So we're not quite there yet, but I think we're on the way. Is that one of the things that you really need when you listen, trying to understand things, is the context of the speech. So this is the scenario where you're at a cocktail party. You walk into the room, everyone chatting like what we're doing in the foyer there, right? And you can't really understand anything until you see your friend right there, Charlie right there. And you walk up to Charlie and say, hey, I haven't seen you for a while. And all of a sudden, all the sound becomes tuned out. You only focus on Charlie. How do we do that? This is how we do it. And I'll show you that in real time. So the first part of it is wait, stop. Let me explain. Don't get too eager. Is that we take out certain context of it, either the spatial context or the temporal context of speech. So to you, it sounds muffled, no real understanding of it. Then we'll give you actual speech, which will give you the context. Then we're going to play that muffled speech again. And all of a sudden, magically, your brain tunes into it. You will understand that cocktail speech. Okay, now you can play. Wait, go back. Play the video. Yes.
Bagpipes and bongos are musical instruments. Bagpipes and bongos are musical instruments. Bagpipes and bongos are musical instruments. The high security prison was surrounded by barbed
Can you turn it
wire.
louder?
The high security prison was surrounded by barbed wire. The high security prison was surrounded by barbed wire.
The full moon shone brightly that night. Move the garbage nearer to the large window.
Okay? So what we found was that these areas of the brain, in the primary auditory cortex, within sub-seconds, tune an understandable garbled speech into understandable speech. And we found the mechanism inside the brain. How do we do that? So now if you take those two things together, one day we may be able to produce a brain decoder that allows people who can't speak to speak by just imagining the speech. Okay. All right, who likes to gamble? Who has been to Las Vegas? Julie, I know you've been there, right? Yeah. All right. So, all kidding aside, addiction is a huge problem. And one of the big problems with addiction that feeds addiction is what? The feeling of regret. I should have bet it. If I bet it, I would have done something, right? So where is the brain signal for regret? It's in this area in the bottom of your brain called the orbital frontal cortex. This area is important for reward and regret. And so we play this little slot machine game with our patients with electrodes in the orbital frontal area. And what we did was we asked them, here's the $10, you can keep it, it's a sure bet. Or you can bet $30 if the next number come up to be bigger. Now, if it's 4, you have 5 other numbers in a single digit that'll be bigger. So it's a reasonable bet, right? Ani, would you bet that? Yeah? Okay. All right, he will bet, okay? But if it's 8, it'll be a stupid bet, right? Because there was only... All right. But what we see is that there are areas of here that are sort of peppered all over the place, which tells you whether you should bet or not. That's a signal. But there's also areas that tell you a regret signal. And I'll show you in real time, in 2 seconds, what the regret signal looks like. So here it is, the electrodes. You can play the video. Here it is, it's coming. Boom, there's your regret. You just regret that you should have bet it, that because you just lost. Okay. And that's the idea, that we need to figure out these regret signals because we need to correct it, because regret feeds addiction, addiction feeds regret, and so forth. This is a vicious cycle. Okay. Okay, the last experiment I want to show is sleep. Because remember, our patient couldn't sleep. And in fact, all of us will not sleep well as we age. It's part of aging. What we found in this study, and this is Randolph who did this study, is that as the brain age, these brain waves become decoupled. There are two very important type of brain wave. One are these slow oscillations that come from the frontal area of the brain, the middle frontal area of the brain. The other is called sleep spindles, and those come from the deep part of the brain called the thalamus. They have to communicate and couple with each other in a precise fashion for us to consolidate memory. If they don't couple, memory during sleep they won't happen. And we all need sleep in order to consolidate memory. So he took a bunch of people who are older. They are healthy older people. Now, they don't have Alzheimer's. And some people who are a bunch of young people. What he has found is that this coupling in the older people occurs slightly off base, slightly off on the center of the slow wave, the blue. While young people occurs right at the center of the slow wave. And this uncoupling just by a few degrees. See, this is older by just about maybe what, 15 degrees or 20, just slightly off. Whereas the younger, it's precisely at the tip. The degree of offset predicted the next day's memory. And not only that, the degree of the offset from that optimal coupling in sleep also related to the brain atrophy in the frontal lobe. And so now we actually have, in the process we already have a device that before you go to sleep, we put on you and we increases the amount of slow wave. You have to wear for 15 minutes while you're brushing your teeth and so forth. And then the amount of slow, so if you have more slow wave, then the idea is that there's more chance for these spindles to couple. So we'll see if that improves it, but that's a non-invasive way of inducing slow wave before you go to sleep. So back to our friend. So this is the happy story. She's no longer sleepless. She hasn't had a seizure. So wait. In fact, Jasmine is right here. Jasmine, you want to stand up? So Jasmine will start a brand new job as a teacher. She's driving now. She's been seizure-free for a year, and she beat all the odds. And I can't take a lot of credit for it because it's her decision whether she want to go for this or not. And if I was in her place, I don't know if I could be brave enough to say, I'll take the weakness over the seizure. But she did. She gambled, she won, and she has no regret. So but why are we here? We're here because we want to remember this incredible lady who I had the wonderful and fortunate opportunity to meet Roneet. It's through her generosity that we're here. And the idea is that through people like Jacob and Roneet, that will continue to inspire the next generation of scientists who will do incredible work. And this is the paper that we just published in a very important journal called Neuron. And in this paper, I sincerely thank Roneet for her generosity and the endowment for the generosity that made this type of research possible. Thank you very much.
Thank you, Dr. Lin. That was fascinating. Really great. Thank you. I had a couple takeaways. So I'm in the real estate business, and I realized what was so fascinating about epilepsy is it covers so much brain real estate, that a lot of disorder. So it has such application to so many people who have, potentially many different types of disorders. He covered the spectrum. So that's what I really like about doing my little part, or our little part, to help support Dr. Lin. And then also, it's probably not a good idea to go home to your spouse and say, it's your amygdala that's causing the problem here. So, your overactive amygdala. So, but I was thinking that at some point. I also wanted to thank Phil Anthony as well. Phil, I'm not sure where you are, but thank you for your support for this. It was really great. Thank you. So as Dr. Lin mentioned, he and Roneet had a relationship and they got to know each other. It was really wonderful. Unfortunately, Dr. Akbari and Roneet did not. I mean, he got to know her on a very different level, but I think had they had the opportunity to meet, they really would have hit it off and really would have formed a deep bond, because in many ways there were two peas in a pod, just very, warm and caring and loving and just committed to people and doing the right thing. And Roneet was someone that expressed love and empathy with whomever she came in contact with. And in the short period of time that I've gotten to know Dr. Akbari, I've seen just many of the same characteristics within him. I think by sharing the story about how we met, it will shine a light on some of those wonderful characteristics. So after Roneet's tragic accident, she went into cardiac arrest, and there were these precious minutes that went by in which she lost oxygen to the brain, and it was just a very devastating situation for everyone involved, everyone that loved her and knew her, and something that, as we talked about in the video, I hope no one ever has to go through in their life. And we were faced with some very, very difficult decisions. And even though the care she was getting in the hospital was excellent, we were just so traumatized and faced with these existential choices, and we felt like we needed to get another opinion. And so we were in the waiting room, and a couple family friends were with us who were doctors. And we were discussing the situation, and one of the doctors said, well, UCI is nearby. It's one of the great hospitals. It has a tremendous staff, tremendous research, great neurologists. So why don't we try to find a neurologist there? And so she went online and on her phone and Googled UCI neurology, essentially, and just went through the list of the various doctors there. And then she came across Dr. Yama Akbari, and she started reading his biography and his areas of expertise and focus and research. And not only was he the most appropriate doctor at UCI for Roneet's case, he was the perfect one in terms of where his research was focused. And the other doctor that was in the room immediately got on his laptop, and I think it was around 10 or 11 p.m. at night, and he drafted a very eloquent email to Dr. Akbari talking about the situation, saying, I know you don't know us, but it would really help the family if there's any way you could evaluate her and come and be able to talk to the doctors. And so to make a long story short, he responded to that email at around 11 or 12 that night, close to midnight. And he wanted to know a little bit more about the case, but to kind of cut to the chase, he and I got in contact directly. And I didn't drop any names because I didn't know anyone that knew him. It turned out that subsequently we have a mutual friend in common. But basically, he came the next day. He evaluated Roneet. The doctors were really wonderful in terms of giving him access to her, all the labs, all the reports, and he was very thorough. And after his evaluation of her, he called us into a private room, and he sat down with the family, and he met with us for 2 hours and answered all of our questions, addressed all of our concerns. And at the end of the day, we realized that there was not much vitality left in Roneet from everything we learned from him. And so the choice we had was a stark one, but it was one that was the hardest choice I would ever have to make, I've ever made in my life, along with my family. And so, Roneet basically went out at the peak of her beauty, her vitality, her life, her love. And we really have Dr. Akbari to thank for helping guide us through the choices or lack thereof. And I think at the end of the day, one of the most comforting things we learned is from all of his research that she didn't suffer. And that really, really has helped me kind of process this maybe in a better way than otherwise could. So I just want to say, thank you again for all you did for us, and really appreciate it. I wish you had gotten to know her. As I said, you two would have loved each other, but thank you for all you did, and I just want to turn it over to you, Dr. Akbari. Thank you.
Thank you very much, Gary, for introducing me, and thank you all for being here. Tonight is about Roneet. We're all here because of her, and unfortunately, as Gary mentioned, I only got to meet her after she had cardiac arrest, unfortunately. But through Gary and many of her family who are here, and the friends and family that are out there, I really feel like I've known her. I started reading Gary's blog, and I've learned so much about Roneet. I've talked to him, and I do feel like I've known her for a long time. And this whole tragedy has brought us all together. So I want to dedicate this talk to Roneet's memory, and I especially want to thank Gary and all the family and all the friends for establishing this endowment to carry her legacy on. I'll start with another case of cardiac arrest that I had as an intern. I was fresh out of medical school almost 14 years ago. And this was a young 25-year-old male with depression who attempted to commit suicide. And he was brought to the ER by his parents. Initially, he was very confused. I vividly remember him. It's one of those cases where you never forget the details of. And he was very normal, but he deteriorated very rapidly, and he went into a coma, ended up requiring life support very rapidly. And his blood pressure worsened despite all our efforts, and at 2 a.m. a code blue was called in the hospital, and I was rotating in the ICU. Code blue is basically cardiac arrest. So we initiated CPR for 30 minutes on this young man, barely younger than me, in front of his parents, begging us to do everything we could for their only child. And we didn't succeed. So emotionally very affected by this. It took me a few days to recover, but it really secured my interest in critical care and cardiac arrest. So the top is not working well. Okay, well, what is cardiac arrest? Cardiac arrest is essentially failure of the heart pumping forward. And so normally our hearts beat and it pumps normally. But if a heart attack happens, or a choking or a drowning event happens, a drug overdose, we have cardiac arrest. The blood stops flowing forward. And that's the code blue. 911 is called, bystanders. CPR is initiated, chest compressions, medications, shock, and the heart can regain function. And we're all happy at that moment. It's a very joyous moment. But the problem is that the brain may not recover. And that's the problem. That's the focus of this talk here. So the point is, time is brain. And we need to conduct optimal CPR immediately. So over 500,000 people suffer cardiac arrest just in the States alone. Resuscitation after cardiac arrest occurs. Resuscitation of these patients happens, and only about a third of them actually survive. And of these patients that survive CPR, only about a third of those patients, or 10% of those patients, actually end up having good neurological recovery. And so the question is, why do so many people survive, and why do so many people actually end up with good brain function afterwards? Our goal is to maximize, of the people that survive, to protect their brain as much as possible, and ultimately to save these people from cardiac arrest. So this, for me, was a deeper calling. We all ask, what is the meaning of life? I'm sure everybody asks that question here. But to some of us, like me, we ask, what is the meaning of death? And unfortunately, people like me have to deal with this on a regular basis. And what happens at that transition between life and death? Something that waits all of us in here. And I always ask, what can we do for cardiac arrest if death is unexpected? We're all going to die one day, but if it's unexpected and we're not prepared for it, that's when the tragedy happens. And what can we do during cardiac arrest? What can we do before cardiac arrest to prevent it from happening? And what can we do after successful CPR? And so with this, I made the decision to pursue critical care as my specialty in neurology. So in neurocritical care training, we have to take care of all types of acute brain injury, strokes, hemorrhages, traumatic brain injuries, spinal cord injury. We take care of all that. Cardiac arrest is one of those, because it's the most devastating of all these. And sometimes a CAT scan like this may look normal, but it's actually very abnormal, because nothing gets worse than death. So why do so few survive cardiac arrest? Well, the first is the time delay to CPR, as I mentioned. But CPR actually hasn't changed for over 50 years since it was developed. We basically do the same thing: chest compressions, epinephrine, help the patient breathe, and sometimes give shock. And that's pretty much it, different combinations of that. The focus is on the heart always. And it's usually a cookie-cutter approach, one size fits all. We give 1 milligram of epinephrine whether you're 400 pounds or 100 pounds. And we have an inability to pause ongoing brain damage. And if we're successful, if we're lucky to bring somebody back, the only treatment we have is actually dropping them by 1 degree from 37 degrees to 36 degrees, which I think in 2019 is pitiful. If that's all we can do to improve them just a little bit, that's inadequate. We need to improve our diagnostic, assessment, and prognostic tools, which are very antiquated. We basically examine the patient once per hour, leave them 55 minutes without clinical exams, and try to put devices on them to try to monitor them. Do some CAT scans, EEGs, blood tests to help prognose, to allow people like the Carmell family to make a decision. And this requires hours to days. So the goal is to save lives by improving cardiac arrest care and providing the best care possible. And to do that, we need to improve clinical research on humans. Unfortunately, people like me who study cardiac arrest have a very difficult time doing this kind of clinical research because it happens suddenly. We can't enroll patients and get their consent during that moment. So we have to use animal models to try to simulate that situation, bring it back to clinical research, something called translational research. We go from the animal model back to clinical research to humans. And meanwhile, we educate the next generation, because this may take more than a generation. It's already taken over 50 years, and we haven't changed much at all, to educate the bystanders, healthcare professionals, scientists, which is a major focus of our lab. So in the neuro-ICU, our patients are all under some kind of multiple types of life support, multiple organs failing. When we have a heart attack, we complain about our heart, of chest pain, for example, but our patients are in a coma. We have to be their voice. So we have to put devices on to help their voices be heard by us. So we have a lot of different monitors on our patients. And that's called multimodal monitoring of comatose patients. So to really study something like cardiac arrest, you need an ICU model. And that's why we decided to make an animal ICU. So we try to simulate everything we can, and we hook up the rat to a bunch of different devices, make it look just like an animal ICU. So we take what we can in the neuro ICU with our patients, our doctors, fellows, nurses, medical students, and we raise questions, like the question we're asking right now. And we have our animal ICU, our rodent, mouse, or rat ICU, and we have here a team of MDs, PhDs, surgical specialists, college students. We record all their brain activity, and then we do what's called signal processing, which require a lot of training by PhD-trained people who code and program statistics, and graduate students and undergraduates. We also look at what's happening at the cellular level into the mechanisms. We look into the brain, we look at gene expression, we look at proteins that are changing. And then we take our questions back and we try to do clinical research. And while we're doing that, we're trying to improve device development, because it really boils down to getting better devices that can detect and allow us to help people. So in our model, We measure all the blood flow in the brain, the cerebral blood flow, brain oxygenation, metabolism, how the brain couples. We measure brainwave activity. We measure blood pressure. We measure all the serum blood, the hemoglobin, sodium levels, all that stuff instantly. Within 2 minutes, we get all those values, just like an ICU, much faster than a hospital ICU. We assess their memory function after they recover. We look at expression of genes and proteins as well. And so to study cardiac arrest, we have to implant electrodes onto their brain. And we use very sophisticated equipment, lasers and lights that shine on the brain while the rat undergoes cardiac arrest. We induce cardiac arrest in all the types of ways that happen. We stop the heart, complete standstill, and then we bring back the heart. We bring back the animal alive. We perform CPR just like we do in humans. We do chest compressions, we inject medications, we'll shock the heart if we have to, and then we monitor the brain as that's happening. When the heart's in a standstill, everything is flat here. This is brain activity here. It looks completely flat. But after CPR, about 45 minutes later, you can see that the brain activity is restarting here. The blood pressure looks pretty good, 153/86. 449, which is normal for a rat. EKG activity looks pretty good. But the rat's not normal. We got a lot of work to do. So in our lab, we study things before cardiac arrest, we study things during cardiac arrest, the moment of death, while the rat remains dead, and then after cardiac arrest. We have a lot of studies going on. I'm not going to bore you through all the details, but we look at particular things like caloric restriction. 18 hours of caloric restriction can actually make a big difference in survival in cardiac arrest. We look at markers of consciousness when the animal's dead, and we look at medications and treatments subsequent to successful CPR, how we can maximize and improve recovery, and how the brain recovers. How do we wake up from an unconscious state to a conscious state? We look at all of those things. So this is not easy to do, as you can imagine. I'm going to focus just mostly on what happens during cardiac arrest and immediately after cardiac arrest for this talk. So what happens when we're dying? Is there brain activity in our brains when we're dead? And if so, what is its significance? Is it good or is it bad? Is it painful? Is it euphoric? That's part of our interests. For me, it's a personal interest. These are my patients that we have to treat while they're dead. We're trying to bring them back alive. And so we're trying to understand consciousness at the basic elemental level. So when I was building the lab, there were a lot of stories, papers being published on activity in the brain during death. So multiple papers were coming out within the past 4 or 5 years, and I was very interested in this. And they call these sort of near-death experiences, that when an animal is dying, there may be some kind of activity going on, bursts of activity, of connections in the brain happening, much more enormous than when we're awake. A month ago, there was a paper published that made the headlines. Some of you may have heard about this, but they took pig brains that were decapitated for food at a farm. And 10 hours after decapitation, brain activity was detected in these brains at Yale University. So this really questions our definition of death. This is a paper published 10 years ago that shows that patients, humans, dying in a sort of monitor called a BIS monitor, which is sort of a poor man's EEG. As the patients are dying, there's this burst of activity occurring. 4 different patients. So something is happening when we're dying. The problem with cases like these, and all the cases I showed you on the last slide, is they don't resuscitate the animals. Our lab has the unique ability to actually bring back these animals. You know, it's not hard to euthanize an animal and record brain activity, but it's very hard to bring it back alive. So what is near-death experience? So 10% of cardiac arrest survivors experience this. I didn't believe it until I started having patients actually tell me about this experience. So in the world, it's unanimous, 10% of all cardiac arrest survivors. The others may be experiencing it, they may just not be reporting it or remembering it. And it's described as vivid imagery during death, seeing loved ones, light at the end of the tunnel, euphoria usually, out-of-body sensation, very enhanced cognitive skills. And it's reported even when the EEG is flat, which is very striking. And very famous people, best-selling authors, neurosurgeons, have actually experienced this and have written about this. And so we don't know why this happens, and we're interested in why this happens. What does this mean? So to do this, we need to study quantitative EEG and connections in the brain. We call that brain connectivity. So Dr. Lin just mentioned in the last talk about different types of how the swings are harmonic. And that's called synchrony, or what we can call coherence. And that's one of the things we're interested in, how different parts of the brain talk to each other. Typically in the ICU, we measure what's called delta through beta bands. So when we're in the hospital, we're looking at EEGs of patients. Those are the typical ones we measure. But in our lab, we look at stuff that's much faster than that, called gamma range. Gamma band EEG is important because it's associated with cognition, deep meditation, and consciousness as well. We're interested in that. And we're interested in that synchrony, that coherence, the swings happening, because that is associated as well with cognition and memory, just like you guys heard from Dr. Lin. And to do this, we need to do quantitative EEG analysis on animals and patients. So this is an experiment in our laboratory. The animal undergoes cardiac arrest. The beginning of anoxia begins with this black line here. So anoxia segment 1, 2, 3, 4. And you can see the blood pressure declines as soon as the anoxia happens. And you can see the brain activity goes silent within about 30 to 45 seconds. The animal's unconscious. And it looks like it's pretty flat here for this segment here, but it actually isn't flat because you can tell over here is really flat. And we're interested in what happens at that gateway between here and here. And what we found was that there's a tremendous amount of coherence or synchrony that occurs at that moment. And so I'll just focus on this top left figure here. But we see that when the animal's awake, actually, it doesn't have that much synchrony. But when it's dying, it has this massive amount. So this may not look large from the audience, but this is huge. It's tenfold higher, maybe more than that, than when the animal's awake, actually. So something massive is happening in the brain when we're dying. And it's very impressive when we look at this data as scientists. This is one of my patients who passed away from cardiac arrest. Luckily, he was resuscitated and came back alive. But you can see the same type of pattern here as he went into cardiac arrest, right when the EEG was going flat. And this lasted a good couple of minutes before CPR was done, which is this other red marks here. There's another patient who passed away from cardiac arrest, one of my patients here as well. And this patient was much older, did not want to be resuscitated, which we always honor. But she had likewise had this sort of synchronous, this massive wave of brain connectivity happening that lasted a good minute or two when her brain activity was flat. So something real is happening. And our question is, what is this? We can detect it now. And we're interested in determining whether this is this happiness, is this euphoria, is this memory? And through a combination of what we do and sort of what Dr. Lin does, that's what I think we can achieve in the future. One of the things we need to do to achieve that type of goal is to have major equipment that can analyze the brain. And so here, initially with the collaboration with the Beckman Laser Institute at UCI, Professor Bruce Stromberg and Bernard Choi, and people in their lab, Dr. Wilson, Dr. Christian Cruzet, custom made a device that brings a laser and another light to be able to really measure the blood flow and metabolism of the brain. And so here's an experiment that shows the animal going into cardiac arrest, flatlining completely here. You can see what's happening inside the brain. Even though the brain activity is flat here, there's immense change going in the brain, up and down, which we don't typically measure because ECOG or EEG doesn't measure that. But it's a highly dynamic state. Even when we see flatlining, the brain is very alive and very active. And that's our goal, is to determine what's happening over here using fancy equipment. So that surge of brain connectivity is shown here. As the animal's dying here, the blood flow goes down. This bump may not seem like a big bump to you, but when you're free falling from the sky and something pushes you the opposite direction, it's big. So whatever it is, it's demanding a lot of blood flow and metabolism as well. So we see it in the brain waves and in our brain connectivity and in our cerebral blood flow measurements. While consciousness is very important, if you wait another minute or two after those waves of this big burst of connectivity, we see something else. So subsequent to that, so that what I showed you earlier was this transition from active EEG to sort of flat EEG, I would see something else in my patients in the ICU. This little blip, and I always thought that was artifact. I didn't know what it was. We brought this data to our lab, we anonymized it, we looked at it, and we saw that they were gigantic when we filtered these waves. They're real. We've had multiple patients like this now. They look like tsunamis. In fact, that's exactly what they're called, tsunamis. Brain tsunamis are real. So I was introduced to this whole field because people looked at it from a different angle, but I was looking at it from cardiac arrest. So these brain tsunamis, many people in the world study these. Their technical term is called spreading depolarizations. And so I started learning about spreading depolarizations, realizing that all my patients are having them when they're dying. What is a spreading depolarization or a brain tsunami? It's a self-propagating wave, very slow, but it happens throughout the brain. And it's the largest, most energy-demanding process known to us in live tissue. In fact, it's 10 times more energy-consuming than seizures. So this is powerful, whatever it happens. And actually, it's considered harmless in a normal state, such as when people have migraines. Many people with migraines have these kind of brain tsunamis. They'll see auras, they'll see, their visual pattern will change. They're very powerful. So if anybody has migraines or anybody knows people have migraines with auras, they're very powerful. But when they happen in an ischemic state or lack of blood flow state, they can actually be very harmful. And that was what I was seeing because this is a state of cardiac arrest. So we looked at our own animals and we saw that while the brain is flat, and again, this is the transition that I was showing you earlier with huge coherence surges and brain connectivity surges. The rest of it's flat, but when we filter that data, we noticed a similar type of wave on every single animal that gets it, on multiple different modalities. And in fact, thanks to Dr. Rob Wilson, a physicist in our lab, and Dr. Christian Cruzet, a biomedical engineer in our lab, we're able to actually see those waves visually through instruments. They're very impressive. And they happen usually once. Here it's just repeating. But it's very impressive when it does happen. So what do these tsunamis mean? What do they mean for CPR? Are they good, bad, or anything? So we looked at the outcome of these animals. And we assessed them. We shined light in their eye. We assessed their walking, their ability to, use their arms and legs, their motor function. And 70 is a perfect score for the animal. 0 is dead, basically. So we assessed the next day, 24 hours later, what these waves might mean. And what we found was that the earlier these waves happen during cardiac arrest, the better the animals are the next day. In fact, if they happen 1.8 minutes after the onset of anoxia, the rats were almost normal the next day. But if you wait 1 minute extra, the rats are almost dead the next day. So this looks like a wave that the earlier it happens, the better. Maybe it's a protective wave. At the minimum, we know it's a prognostic wave because we can predict with 82% accuracy whether the animal is going to be good or bad the next day in real time. But after CPR, we actually see another wave. That's not as obvious here. It's a little slower here. And we can detect it in our optical imaging again. It's a very impressive wave after successful CPR. And we saw, well, what does this wave mean? This is called a repolarization after CPR. And we found the same thing. The earlier this wave happens, if it happens 0.6 minutes, so almost 30 to 40 seconds after successful CPR, the animals are almost normal the next day. But if you wait 1 extra minute, the animals are almost dead the next day. So there's another wave that can predict it. In fact, when we combine the spreading depolarization, the brain tsunami during cardiac arrest and the tsunami after CPR, we have over 91% accuracy to determine whether the animal is going to be good or bad the next day. So what does this mean? This means that in animals, we can capture these brainwaves. If we capture these brainwaves during cardiac arrest or after CPR, we can predict with over 90% accuracy whether the animal is going to be good or bad. So as a neurointensive care doctor, for me, I imagine what this could mean for my patients, right? I mean, we can at least capture the CPR, the post-CPR phase. So could this be an innate protective wave, which is one possibility? And if so, can we harness this energy and give it to patients? Administer this earlier. There are ways we can administer this wave. It's very easy, actually, to administer this wave. The spreading depolarization is caused by touching the brain, giving electric shock to the brain, magnetic stimulation, many different ways. It's actually very easy to give this wave. And so we ask in our lab if we can shock the heart, which sounded crazy 50 years ago or 100 years ago. Why can't we shock the brain too? And that's one of the interests that we have. So the goals of our lab are to really transform standard CPR to advanced brain-heart CPR. We want to revolutionize treatments, critical care after CPR. We want to develop devices that will allow us and equip first responders, EMTs, paramedics, emergency medicine doctors, nurses, and the ICU doctors to be able to rapidly make a diagnosis, prognosis, and to guide the doctors and nurses to change their treatments. We also want to understand the dying process and near-death experience. What do we feel when we're dying? And how can we comfort the dying patient who wants to die, who's ready to die? So to answer these questions, we've received a grant recently to start our first clinical research study to do exactly that, funded by Hamamatsu. We're the first institution to use time-resolved spectroscopy in the ICU on our patients, where it's a non-invasive device, we just slap it on, and we can measure these types of waves. And so we have a lot of work to do, because this is just beginning. But we also need ultra-portable brainwave detecting devices, like EEG devices. We want to minimize this huge power that we use to do EEGs into a small portable device, where we can enable people to have rapid diagnoses and preliminary assessments in the field, and in the ER, and in the ICU. And so we're also developing ultra-portable EEG systems, a pen EEG, if you may, to be able to allow us to do this. So with that, I want to leave you with a more recent case. Almost 10 years later, after the first case that I showed you, this was a 23-year-old female who was completely normal but developed autoimmune encephalitis, which we see, unfortunately, quite a bit, who ended up developing seizures as a consequence to this encephalitis. And she worsened to having uncontrolled seizures, ended up going into a medically induced coma for 2 months, medically induced coma. She was maximized on 5 anti-epileptic medications, barbiturate coma. It's the deepest type of medically induced coma that we have. And when you're on a lot of these medications, your blood pressure goes down, it drops a lot. And so she had to be on other medications to keep her blood pressures up, what we call vasopressors. So multiple medications, 10 different drips. And her blood pressure dropped. And it dropped right after we had rounded on her, maybe an hour or two after we'd rounded on her. She had a cardiac arrest. We were just 20 feet down from her onto a couple of the other patients. Code Blue was called. We ran immediately to her. We knew her. We just rounded on her an hour ago. We did CPR in front of her father. So the worst type of CPR I like to do. And we resuscitated her. I had a talk with the father. As soon as I finished the talk, half an hour later, she coded again. We did CPR on her again. We brought her back again. I told the father, I don't think you should go home. You should stay here. In fact, I told him to bring the rest of the family in because I didn't think it was going to turn out well. But we were very fortunate. She stabilized over the next few days. She woke up from her coma. She went to a nursing facility. She had a tracheostomy. And she came back in a wheelchair and visited us. And I called her yesterday. And I told her that, and unfortunately, they couldn't be here today. But I said, how's she doing? She wasn't there when I called her. Her dad said, he instantly remembered me. And I said, send me some pictures of her. And so she's doing wonderful. This is her, and this is her daughter. She gets to spend every day with her daughter and her dad and her younger siblings. And what makes this possible are the wonderful nurses that we have and the whole team that we have. The doctors, but the nurses are really key in this situation. Everybody, we work as a team. Each member of the team is important. And it goes the same for the hospital and the same with the lab. And the data that I've shown you would never be possible because I'm just a coach. I just bring a good team together. And we have a lot of doctors, clinicians like Dr. Mackey, Dr. Rafi. We have molecular biologists like Dr. Tian, physicists like Dr. Wilson, biomedical engineers like Dr. Cruzette, Kelly, who's joined us more recently, and a lot of other people that make a difference. Mateen and Afshin helped me build this lab from the get-go. Mateen's going to be starting his MD PhD program at Stanford in a few months. So I'm just honored to work with these kind of people. Many of them are volunteers, by the way, who dedicate their time because they share our passion for the type of work that we do. And we work as a team together, and every team member and every coach like me needs a mentor. And so I've had the honor of receiving mentorship from Professor Bruce Tromberg, who's at NIH, one of the directors at NIH now, Professor Osteward and Bernard Choi, Lilith Manatskani, one of our epileptologists and breath loper. The funding that's made this possible by NIH is important. I want to thank the Research Associates Award, which was founded and supported by the Swindons, Miss Madeline Swindon, Mr. Jim Irvine Swindon. And most importantly, I want to thank Gary for establishing the Roneet Carmell Memorial Endowment Fund because we're going to carry Roneet's legacy on and honor her by doing the best work that we can. So thank you all for being here, and thank you, Gary.
We have our doctors. We had some note cards in there. If you have any questions, or you can just raise your hands and they can bring a microphone over.
Yes, they occur during all types of acute brain injury. Well, first of all, they can occur during migraines when we're completely normal, but they occur during strokes, during hemorrhages, anything that has affected the brain. Surgeons can actually cause it by just touching the brain. They can cause the wave to occur as well. In fact, even insects get this. This is a highly conserved process, which is why we believe it's very important.
Anybody else? Does the effect of morphine in a dying elderly patient affect the brain tsunamis?
You ask the best question. This is a question that I ask every day, to be honest with you, because most people who suffer cardiac arrest, at least the people who've had near-death experiences, do not complain about it being a painful process. It's a very controversial area. We don't know the right answer. So standard of care is that we give morphine to patients, which we do every day, and not just morphine, but actually benzodiazepines, kind of like Xanax or Versed or Ativan. So we do that standard, but that is one very important question. Does it affect? And we don't know whether it affects these types of activity that I've shown you here. It certainly suppresses the brain function, no question about that. But we don't know if it's suppressing the good stuff or the bad stuff. She was on a little bit of morphine and a little bit of Versed. That's correct. That's right.
Dr. Akbari, regarding CPR, what is more effective, 30 compressions and 2 rescue breaths, or continual chest compressions?
That's a good question. So if you have 2 people, then clearly both should be done. 30 breaths and 30 compressions and 2 breaths. If only one person is done, the guidelines state to just do the 30 plus 2, but there's controversy around that. And so some people just perform CPR, just compressions. In fact, sometimes by compressing, every time we're compressing, you get a little bit of breathing going on because it compresses the lungs as well as the heart. But that's exactly the type of research that needs to be done to be able to conduct and compare those 2 things side by side. That's why it makes it very difficult and challenging to study this kind of process.
So at this point, what would your recommendation be for all of us who might encounter a moment where we need to perform CPR, 30 and 2?
Yeah, I mean, ACLS guidelines still recommend 30 and 2.
And then you mentioned the epinephrine, which is an EpiPen. Is it always in the form of an EpiPen?
Yeah, The epinephrine that we give is all intravenous, and so you have to have intravenous access to give it.
So not an EpiPen for the allergies?
No, then that's a good question. It hasn't been tested during cardiac arrest to give an EpiPen, because you certainly will get some effect with an EpiPen. That's a very good question.
So at this point, would you say utilize an EpiPen?
No, I wouldn't recommend that.
Thank you. Thank you, doctor.
I'll get in trouble. I have my thoughts, but I'll get in trouble if I say them.
Thank you, doctor.
I can share with you privately what I would do if I were at home, but I can talk to you about that later.
Can they ever do like electrodes or something that just sort of kills that part, or do you always have to, physically remove the portion of the brain that's causing the seizures? Or maybe you don't.
So
maybe the researchers.
it may sound crude, to remove a part of the brain, but the idea is that if the brain is causing the problem, if you don't remove the root of the problem, then the seizure will never stop. People have tried all kinds of different ways of not removing the brain. So there's actually a device called a responsive neurostimulator where they put in the brain to detect the seizure and to send an electrical shock. Theoretically, that sounds great, but the chance of you being seizure-free with that device is actually fairly low. For Jasmine, if I may say, we actually did put in the responsive neurostimulator because we weren't sure we're trying to take the minimum amount of brain tissue out, but not causing the deficit such as weakness. So we actually put in the brain stimulator around the area just as an insurance. And luckily, now we can actually lively monitor. Right now, I can tap into your brain with my little phone. And in fact, we don't see any seizures.
So in epilepsy in general, though, it's not necessarily just one portion of the brain that you would focus on. It could happen, each patient is different.
Each patient is different. It can happen in different areas, and different areas have different challenges. So if it's like a temporal lobe, you worry about memory and naming. If it's frontal lobe, you worry about motor and executive functions such as thinking and decision making. Every part of the brain is slightly different.
Thank you.
This is for Dr. Lin. So when you're trying to find the needle in the haystack, are you just guessing, or do you have a specific protocol for where you're trying to find that needle pretty much?
Well, this is the whole reason why I went into epilepsy and the related research is because, we actually have to listen to the patient and listen to what the seizure look like. And the patient's story actually tells you what most likely the seizure is. I mean, Jasmine, when she came and saw me, and her mom sort of demonstrated this ballerina pose, and I didn't believe that actually. And surely enough, you saw the video. Indeed, that's what she does. That is likely an area called the supplementary motor cortex, where the planning motor is. But which side is a little bit hard to decipher. And the problem with that type of seizure is that it's very deep inside the frontal lobe, so you can't see it on the surface EEG. And so that's why it was so challenging. But we have something called hypothesis, and this is where we don't put all the needle electrodes everywhere, but we survey it first with a good hypothesis.
I have a question about back to the amygdala. So if someone is predisposed to anxiety and stress, that obviously there's a lot of ramifications for that, but you were showing that the circuitry really only flows one way in that under that circumstance, or?
Yeah. So we think that we discovered this overactive amygdala communicating to the memory. So if you the amygdala overactive, then you're laying down emotional memory that could be reactivated later, and that could be the cause of the trouble. What's very interesting, and these waves are very stereotypic. So the idea is that if you send another wave in the brain by electrical stimulation that goes against the wave in a different phase, then you could cancel out this type of communication. So what we're trying to do is actually that's sort of a big dream of the lab, and these guys who are from my lab understand this, is that we want to detect that over-emotionality in real time and send electrical stimulation that reverse that in real time so that people don't experience this type of experience.
Is there anything you can do through meditation or mindfulness or anything like that? Or are you looking at extreme situations?
Well, I'm pretty extreme because I think that there's a lot about the wellness aspect of it. I mean, there's some good literature about, being able to, there are, the mind and the brain, it's an incredible thing. And I think that's what Yama and I have shared in common is that, yes, through meditation, you can change the rhythm of these waves. Through medication, you can, through biofeedback, there are things that you can do to sort of dial down the amygdala, if you would.
I'll add to that. There's actually a very recent evidence, very new evidence that shows that the way we breathe actually affects not only the brainwave activity, but how our brains clear bad stuff in our brain. So that's something called the glymphatic system and the lymphatic system. So our breathing is actually very critical. And so we believe, my next guess is that there's going to be shown that the pattern of breathing in meditation is going to be affecting how our brains actually clear like all the bad chemicals basically and make us feel better essentially rapidly.
So on that note, will mindfulness and or meditation, since it can slow down the brain waves, also help with sleep because the slow brain waves during sleep give you a better restful sleep and also help memory? Is there a correlation?
I'm sure there is. It's those type of studies are a bit hard to do in control settings scientifically, but I think that there are a lot of ways, natural ways of improving your lifestyle that don't need to get to the extreme. But for those people who can't have that, who it doesn't work, then you have to go to the next level. And usually that's what happens in people who are experiencing these disabling disorders such as depression and so forth.
I don't know how this may figure into the work that you're actually doing, but are you doing work with transcranial magnetic pulse and low-level DC transcranial stimulation?
So, that's exactly what we're doing in the last experiment with the sleep, is a transcranial alternating stimulation to the forehead to increase the slow wave before people go to sleep. So that's exactly, but it's a small device. The amount of electricity is you can use 2 AA battery, put in your pocket, and then, so it's a very small amount of electricity. But the incredible thing is that very little electricity can induce profound changes in your brain from the outside.
I get from that you're achieving some very positive results with this.
Yeah, probably not good enough. Right now we're looking at, we have a sleep lab in Berkeley. So it's a company, but we're getting about 15 to 20% increase in the slow wave with the stimulation 15 minutes before you go to sleep. But I don't know if 15 to 20% is good enough to achieve the goals. We're trying to optimize that. But yeah, you can. There are real statistical, real changes with the brainwave if you.
And one more thing. An article came across my desk this morning about the use of xenon gas in traumatic brain injuries. Are you familiar with that?
A little bit. That's been actually studied for quite a while. Not just xenon gas, but many other gases. And the goal is to protect the brain when there's an acute brain injury occurring. So there's some evidence to support different versions, not just xenon, but other types of gases, even hydrogen sulfide, to try to induce a suspended animation or to provide more blood flow to the brain, to vasodilate the brain. Those are ongoing studies. And I do want to mention that the transcranial magnetic stimulation and transcranial direct current stimulation, those things actually cause the brain tsunamis that I was mentioning. So there's that bridge between us that I believe that's one of our planned studies, is to induce these kind of brain tsunamis through the same types of techniques that Dr. Lin is using to study memory and emotion as well. But there are a lot of studies ongoing. It's just what I do in cardiac arrest is a little bit more challenging to study because it happens very unexpectedly.
Okay, thank you, everyone. Thank you, Dr. Akbari, Dr. Lin, Gary. And one last slide. These are all the donors that have given to the Roneet Carmell Endowment and the previous fund. It's been an incredible outpouring of support for the work of our doctors, and I just wanted to thank everyone. Some of you have given already. And if you are interested in supporting either one of the research studies you just heard about, these are the online URL links, or you can find me. I'll be out in the reception. So I wanted to welcome everyone now to the reception out there. We have lots of food, so please make yourself at home with drink and everything. And thank you.